Hello everyone. Welcome to CeDAR LightHouse project program of second edition. Today we're going to show a technical demonstration of graph neural networks. Myself, Roopesh Bharatwaj K R, and with my colleague Alireza. Let's give a brief introduction to the graph data. Graph data refers to data that is organized and represented using a graph structure format. A graph is a collection of nodes, also known as vertices, connected by an edge. Graph data can describe relationship, connections, or the interaction between the entities. Let's think of a social network like Facebook in our example, where each user, Ram, Amir, and Sita is a node, and each connection between the users, such as a friendship or a wife, is an edge. Likewise, the further examples shown in the in our text here is like movie graph data, transport navigation data, and chemical reactions data. These can be used using a graph data. Graph convolution network uses a convolutional graph operation to aggregate informations from a node's neighbor and generate a new representation from the node. This operation can be applied to multiple neural network layers to learn increasingly complex representation. This can be used for tasks such as like a node classification, a link prediction, and graph generation, and overall for a recommendation system. The graph ML applications are broadly classified into four major categories based on the level at which the predictions are made. They are graph level predictions, node level prediction, edge level prediction, and subgraph level prediction. The graph level predictions involves predicting the properties of the entire graph rather than individual nodes or edges. The node level predictions involve predicting the properties of individual nodes in a graph, such as predicting the category of a node or predicting its degree of centrality. Edge level prediction involves predicting the properties of individual edge in a graph, such as predicting the presence of a link between two nodes or predicting the type of relationship between them. Subgraph level prediction involves predicting the properties of subgraph with a larger graph, such as predicting the existing of certain patterns or motif in the graph. The link prediction in graph neural networks is a task that involves predicting the likelihood of a connection or edge between two nodes in a graph. It is a fundamental problem in graph analysis and has various applications including social network analysis, recommendation building, biological network analysis, and much more. Let's start the journey towards a link prediction of remote working hub use case. Remote working hub across the entire Dublin and its connected amenities. The project architecture of graph machine learning based link prediction has been divided into four building blocks. They are data engineering, graph engineering, Neo4j graph data science, and prediction of scores. Let's get deep into each and every building blocks of this architecture. Data engineering is an important phase of an ML pipeline where data undergoes several stages of cleaning and feature enhancement. Likewise, here we have GeoJSON raw data which contains half a million records of latitudes and longitudes of remote working hub across Ireland and all the different amenities across each and every hubs such as the banks, ATMs, restaurants, bar, cafe, bicycle parking, supermarkets, shopping centers and rental shops. Since we have a lot of missing information about the location, like missing of latitudes and longitude, we used a GeoPy, a Python library. Using a reverse encoding strategy, we were able to find out the name, address, air code, and specific latitude and longitude of that address. Graph engineering is one of the complex and challenging tasks as we need to set up a nodes and edges along the properties for the dataset, like remote working hub and other 14 amenities datasets. Each hub and amenity is a node, and the connection between each edge are the relationship. Each hub has its own properties that are like attributes like latitude, longitude, name, air code, address, and special informations and other features and contact information of all specific details of each hub. Likewise, we have the node attributes or properties of each amenities as well, which contains the air code, name, latitude, longitude, and their addresses. Now, the biggest challenge is we have converted our data of tableau data of graphical format using like nodes and edges. How these nodes and edges can be interconnected with each other. So now we have taken consideration of only the Dublin specific area, and each Dublin area has their own specific set of error codes. say like D07 E321. So D07 is a specific set of zones and E321 is a specific private place of an amenity. So we have mapped the sectors of the Dublin right from D1 to D23. We have mapped it together along with the specific set of hubs of that same region and same set of amenities. Like this, we have grouped around like 78 hubs and 1300 amenities. From this graph visualization, we can see that there are 1154 nodes which have all hubs and amenities connected using the Dublin zones and their individual air codes, and 996 relationships connecting the amenities. Neo4j Graph Data Science is an extension and library for Neo4j Graph Database. It is designed to empower data scientists and analysts to perform advanced graph analytics and machine learning directly within the Neo4j environment. This extension provides a comprehensive set of tools and algorithms specifically tailored for working with graph data. It includes a wider range of algorithms for tasks such as community detection, centrality analysis, pathfinding, and more. Additionally, it supports the execution of custom graph algorithms, allowing for tailored analysis based on specific use cases. Neo4j graph data science is especially beneficial in scenarios where data relationship plays a crucial role, such as a social network recommendation, fraud detection, and knowledge graph analysis. By harnessing the power of graph analytics, data scientists can uncover valuable insights and patterns within complex interconnected datasets. There are various measures or algorithms used in graph analytics, particularly for link prediction and community detection. Here are a brief description of each and every algorithm. ADMIC-ADAR. ADMIC-ADAR algorithm measures the closeness of a node in a social network based on the number of shared neighbors they have. It assigns higher importance to shared neighbor that are less common, indicating a potentially stronger connection. Common neighbors. Common neighbor algorithm reflects the idea that two individuals who share a mutual friend are more likely to be introduced to each other. This measures emphasizes the importance of common connections in predicting potential links. Preferential attachment. The preferential attachment algorithm assesses the node closeness based on shared neighbor, particularly applicable in scale-free networks. It operates on the principle that nodes with higher degree are more likely to attract new connections. Resource allocation. The resource allocation algorithm evaluates node closeness by considering shared neighbors. Notably, this measure ensures that many links are not assigned identically scores when one information about nearest neighbor is considered. Same community. The same community algorithm determines whether two nodes belong to the same community within a network. These communities can be identified using a community detection method, and this measure helps assess intra-community connections. Total neighbors. The total neighbor algorithm quantifies nodes' closeness based on the count of unique neighbors they have. It operates on a principle that high connected nodes are more likely to receive a new links. These measures plays a critical role in tasks like link prediction, of suggesting potential connections and determining community structures within a graph. Understanding and appropriately applying these measures is a fundamental in graph analysis, particularly in scenarios like social network recommendation system, community detection in various networks. We have computed graph data science algorithm scores of link prediction and found preferential attachment to be the much more realistic and optimal solution for our specific use case. As preferential attachments are scale-free network, it operates on a principle that nodes with higher degree are more likely to attract a newer connection. The Barabási-Albert model stands as a remarkable algorithm, adept at emulating real-world networks such as Internet, World Wide Web, and intricate social networks. What sets apart is its unique capacity to yield scale-free networks. In these, a select few nodes known as hub boast a multitude of connections, far suppressing the majority. This phenomenon arises from a mechanism known as preferential attachment, endowing a new nodes with a higher inclination to link with already well connected nodes. named after its pioneering creators Albert Larazzo Barbasi and Reka Albert. This model unveils the genesis of these highly interlinked hubs across spectrum of intricate networks. Its broad application spans the realm of computer science, physics, biology, and sociology, underpinning our understanding of complex systems in various domains. This BA model is a pivotal tool in deciphering the structured underpinnings of these multi-factor networks that shape our interconnected world. Using Graph Data Science Library of Neo4j, we have computed all possible combinations around 68,000 records of all hubs connecting the amenities of remote working hub data. From the preferential attachment score, we can see the hub D07CX22 is connected with a bank of D02KX03, which has a score of 25. Similarly, the D07CX22 hub is connected with the Bank of Ireland D02VR66 has a score of 35. Now, these scores will tell you how well is closely connected with each other. As we saw earlier, there are fluctuations of scores in preferential attachment. For further computation, we did a correlation analysis with respect to the scores and the distance between hub and the specific amenities. We computed a Manhattan distance based on the latitude and longitude of like hubs and amenities, and we have verified the same with the Google Distance Matrix API. From these results, we could say that when the distance is short, there is a high preferential attachment scores between hubs and amenities. Based on this, we can tell which amenities are closer to the hubs. From the overall score of entire hubs in Dublin area, we can say which amenities needs to be increased or how can they be profitable if they are established in which specific area. This can be a potential business model or market growth strategy analysis tool for potential organization who wants to establish an organization in the specific community. Furthermore, this can be shaped as a recommended system based on additional user information data with a front-end tool as a scalable application. Thank you very much for watching the technical demonstration of link prediction using graph data science. To know more about the graph neural networks, please watch our playlist.